is obtained as before. You subtract from the numerator a multiple of the denominator. And you try it with different value of lambda. So you start with some feasible solution, you specify lambda 0, and you start the process. At each iteration, you have some value of lambda c, and you solve the associated parametric problem. You get a solution, x, y, and w, okay? And then you check if we can stop the procedure. We stop the procedure whenever this value here gets close to 0. Okay? So whenever we get this quantity close enough to 0, we stop the process. And we accept lambda star as the close to the optimal solution. Okay? Close to the optimal value of the particular function. This is close to the optimal solution, and the value of the grouping efficiency is given by evaluating the efficacy at this period. Otherwise, if we are not close enough to 0, we modify lambda. As we did before, we take the ratio of the numerator divided by the denominator at the value of the point that we have on hand. And we repeat the process. Okay? Good. To make our test, or, well, before I go to this, you see that the main problem is to solve this integer programming problem, binary, at each iteration. So this is not an easy problem to solve. Okay? Dealing with integer programming problem is usually very hard. So to solve this problem, we use an optimizer software available, Cplex. And Cplex was on hand for us, so we use Cplex. Okay. The original solution, we took the original solution as the best known solution for the problem that we want to solve. And we refer to meta-heuristic problems, so we look at the result obtained by the different meta-heuristic available, and we select the one leading to the best known solution. And this happened to be ours when we were doing the test. So we used the best solution that we obtained during the process. Why we did this? Well, we thought that our solution was quite good, so we went to start close to the optimal solution in order to reduce the number of iterations. Because at each iteration, we have to solve this problem. And so we want to reduce the number of times we have to solve the binary linear integer programming problem. Okay? Good. So to make our test, we refer to a set of benchmark problems that people use to compare their results. And we solve this problem on a PC. Now, for these 35 problems, 13 of them were quite easy to solve. So we were able to reach an optimal solution for 13 problems, and each problem it took less than 32 seconds. This is very good because we are dealing with integer programming problems. But 14 other problems we were able to solve them to optimality, but Unfortunately, it took much longer time, okay? Because the problems were larger and they were more difficult to solve. And finally, for 8 problems, we were not able to get an optimal solution because we reached the limit, the memory limit, before we can get to an optimal solution. Okay? So, for 27 problems, we were able to get an optimal solution. Then, comparing with the meta-heuristic solution that we had, we were able, with the meta-heuristic, to get to the optimal solution. Okay? And the time required to solve the problem was a lot more faster using the meta-heuristic. But nevertheless, it was nice to refer to the Dinkelbach algorithm to see how close we can get to an optimal solution when using a meta-heuristic. Okay. This was the interesting part. But of course, as we see here, we should not try to solve large problems with an exact method. You should turn to meta-heuristic method. Okay? Good. So the next step was to try to use the Dinkelbach procedure to improve the meta-heuristic that we developed. Okay? This is a good example of combining, as I said before, exact method with meta-heuristic. Method. How much time left? 15? Ah, very good. Okay. So, the problem that we are solving is the following. So we return to the maximization instead of working with the minimization. Okay. So this is the quadratic binary programming problem that we will solve with the meta-heuristic. Good. So there are all kinds of meta-heuristic. The Dinkelbach procedure was useful within local search algorithm. Okay. Local search algorithm, roughly speaking, are iterative procedure. And at each iteration, you move from a current solution to another solution belonging to what we call the neighborhood of the solution. And doing this, we are moving toward an optimal solution. And this is the basic idea behind local search algorithm. There are other meta-heuristic, population-based meta-heuristic problem, where at each iteration you have a set of feasible solutions. And you modify the set at each iteration to get another set of feasible solutions. These are population-based algorithms. You have genetic algorithm and you have mimetic procedure. For instance, you have the end colony procedure. In this technique, you try to specify different set of feasible solutions, imitating a set of hens moving from their nest to get a place where they can reach to food. Okay? This is a mimetic algorithm. This is quite interesting. But here, I will talk about local search algorithm. Personally, this is the kind of technique that I prefer, but that's a personal comment. Okay, so in these kind of procedure, you see that we have to define what we call the neighborhood. We are not in the continuous context. We are dealing with integer solution. So what do we call the neighborhood of the current solution? And in general, there are a lot of different neighborhoods that we can use. Most of the time, they are specified in terms of the structure of the problem. So you don't use the same kind of neighborhood from one problem to another problem. You specify the neighborhood in terms or closely related to the problem. So the neighborhood that we use in our implementation of local search algorithm, we have different local search algorithms that we were using. And we use a neighborhood that is more difficult to implement than most straightforward neighborhood that we can specify to solve a problem. And the idea was to combine two strategies. So we have a solution on M. The first step is to perturb the solution by eliminating the assignment of the cell to some part or to some machine. And then taking this part or machine and reassign them randomly to different parts, to different cells. This is a very straightforward technique. In terms of meta heuristic, we call this diversification. Okay? We diversify our search. Okay? We look around the physical domain. We modify a solution to get to another point, and then we start to improve the solution from a new point. The second step is to improve the solution that we get in this. We have a technique to improve the solution. In terms of meta-heuristic, we call this intensification. We intensify the search around the point that we have on that. Okay? So let's see the detail of this specification of a solution in the neighborhood of the current solution. Okay? So the first step is to diversify. To diversify, as we said before, we destroy part of the solution to recover the new solution. And in order to do this, we flip the coin. Either we modify family or we modify group. We modify part or we modify machine. Okay? So if we decide to modify, say, the part, then you pick a certain percentage of parts. You eliminate the family where it belongs. And then to get a new solution, you reassign them randomly to different family. Or, well, you do the same using the machine. Now, once you have a new solution, then you intensify. Okay, so if you modify here the part, then you will go to, you have a new assignment of part to family. So we start, okay, we have this, then we will try to modify the assignment of the machine in order to get a better solution. So we modify the machine group in terms of, on the basis of the part family. Now we have new assignment of the part. You move back and you say, okay, I will try to modify the solution, modify the assignment of the part on the basis of the new group. Okay? So I will run between these two processes. And our stopping criterion was to say, okay, we stop whenever the solution on hand cannot be modified. Okay. Remember, this is meta-heuristic. Okay. You have to take decision to stop the process. Okay. You don't refer to optimality. You want to get good solution. So, as you see, this is a straightforward technique to implement. The thing was, how do we modify this? How do we intensify? Okay? So we turn to this problem here. The first process that we used to specify our first set of meta-heuristic was to, in a way, to simulate or to simulate the objective function in such a way to try to improve the objective function by, say, modifying the part on the basis of machine group. This was a very, I would say, quite good approximation of the objective function to improve the solution. But looking at this problem, as you will see, we can use the Dinkelbach procedure. Okay. So the Dinkelbach procedure is an exact procedure. So it should be better to get better. It should be a good technique to get better solution because you use an exact procedure. And we were able to verify this numerically. But this was our intuition. Okay, so let's look at the intensification. And suppose we will look at the problem of modifying the part family on the basis of the machine. So coming back here, modify the part family on the basis of the machine. Okay? And we have the same procedure for modifying the group on the basis of part. Okay. So, suppose the solution on n is denoted by x bar, y bar. Okay. So, coming back to our problem, we fix the assignment of the machine. So we fix x bar. So we fix x bar associated with different group associated with the assignment that we have for the machine. So, assigning x, replacing x by x bar, you see that the problem simplifies. Okay? And we are left with the problem involving only the y variable. Furthermore, the objective function is a ratio, but instead of being quadratic, they are linear, easier to deal with. So, this structure is nice because it's a binary integer programming problem where the objective function is a ratio of two functions. So again, we turn to the Dinkelbach procedure to deal with this. Okay? So, we have the problem, and this is the same trick. Okay, you specify the associated parametric problem. And at each iteration, you specify a new value of lambda. And you have to solve the associated programming problem with a specified lambda to get a new solution, define a new lambda, and you cycle around until the value of the objective function for the associated parametric problem get close to zero. We reapply straightforward the Dinkelbach procedure. Okay? So we can summarize again the Dinkelbach procedure. Okay? Specify y0. Here we take the y bar available. We specify lambda 0. Solve the associated parametric problem. Get you assign a fourth part. Check for optimality. If the optimal value here is close enough to 0, we stop. Otherwise, we modify it. This is a straightforward technique behind Dinkelbach procedure. Okay? Good. So, here the problem to solve is, again, the associated parametric problem. But this problem is very straightforward to solve. Okay? Let me go through rapidly the technique. It is very straightforward. Okay? Under some assumption I would like to. Okay, so I have this problem to solve. Okay? So I can modify the objective function here to put the summation over k outside. Okay? So here I have a problem which is almost separable in terms of the variable yj, except for this one. Okay. Okay, so very rapidly, we make the following assumption. We eliminate these constraints, so the problem is separable. And we solve this problem in a very straightforward fashion. Okay? For each part, you find the cell where it is assigned by evaluating this value here for each k. Then you maximize it, take the one, maximize it. And if you look at this, I won't go into the detail, but if you look at this expression here, okay? Here you have the number of 1 belonging in the row of the set where the machine are assigned to k. And here you have the zeros in the same subset. Okay? And these are very easy to find out just looking at the matrix. Okay, let's see an example. Okay, suppose that we have say 6 and 7 belonging to the first group, 1 and 2 to the second group, and 3, 4, 5 in the third group. Okay? And we want to assign 7 to a family. So we look for each index k equal 1, 2, and 3. And we want to assign 7 to one of the corresponding part. So we look to this quantity for each k. So we look for k equal to 1. We have 2 zeros. Okay, so looking here, we have no one minus lambda times the number of zero, we have 2. If we look at 2, again, 2, 0, so 0 minus 2 lambda. If we look at 3, we have 3, 1. Okay, so we have 2, 1, so we have 2 here, and we have 1, 0 minus lambda times 1. So you see that the best thing to do is to assign y or 7 to family. This is a very straightforward technique. Good. So we use this within stimulated annealing is very good meta heuristic. And at each iteration of the process, you have to generate an element in the neighborhood of the current solution. So we use Dinkelbach procedure to generate a solution in the neighborhood. And the test indicates that we get the best solution using the Dinkelbach procedure compared to the other one that we add on that. Okay. So looking at the 35 benchmark problem with simulated annealing, we were able to reach the optimal solution for the 27 problem that was solved exactly with Dinkelbach procedure. We were able to reach the best known solution in the literature for 4 other problems, and we were able to improve the best solution known for 2 problems. Unfortunately, we missed 2 problems. We didn't reach the best known solution for 2 problems. Okay? So this is a very good, I think, a very good solution procedure, and it ran very fast. We were able to get even better result here by combining a genetic algorithm with with the simulated annealing procedure. But the solution time increased. What we were able to improve more solution, and we were able to reach almost all the best known solutions. Okay. Very good. Thank you.
Some questions? Okay.
These problems are mostly binary, so there are naturally a limitation with dimension. But in the meta-heuristic that you showed, there is a separable fraction which normally avoids this problem dimension. So my question is, up to which dimension is this solvable?
Up to what dimension of problems we can solve? In fact, we were able to solve. I don't remember exactly the size of the problem, but we were able to deal with all the 35 benchmark problems. Some of them were. I don't have the number with me. Some of them were quite large. But other ones were very simple. The 27 here, or I would say the 13 that we solved exactly with Dinkelbach were quite small and easy to solve. Other one, when you increase the dimension, Dinkelbach was not able to solve. But here we were able to reach, well, at least the best known solution in the literature. But unfortunately, I don't remember exactly the number. W, yes, the W, I, J, K.
And then you try to solve the phase. But usually that we can do more big instead of solving directly the approach because it is clear that the case will be phase, but not only because the variables are different. Each phase also because the problem is highly degenerate. I believe that even if you try to solve only the linear relaxation, it will be hard for large instances.
Yes, that's true. Yeah.
Now, perhaps the same idea that you use and when is correct, like the Lagrangian relaxation. I think that this part we can use Lagrangian relaxation when you do this problem.
Yes.
Because if we have linear relaxation, we have some idea about how to begin, for example, local search. We can have a very good solution to begin this local search. If we
Yes.
have that solution.
Yes, yes. We use the other idea. We start from the best known solution, the heuristic solution, to reduce the solution time for the exact procedure. But you are saying that we might put more effort to solve the exact problem to get better approximation, maybe the solution obtained, the first feasible solution that we obtained to start. Yes, yes. Of course, when you solve a problem using meta-heuristic, you can think of all kind of strategy. You can think of all kind of strategy, and the idea is to have the good idea and to implement it. I didn't talk about, I didn't think about this like originally, actually. So it's a good suggestion.
Yeah, perhaps I missed something, but when you settle the last, in the last slide, you settle the reports, the problem, and the formulas, and there was this K, this capital K, which is the number of cells.
Yes, the number of cells.
So, does it mean that you initially suppose a number of cells?
Yes, yes. This is yes. This is an assumption that we make. We fix the number of cells.
But does it make sense? Does it make sense? Because you want to group optimally.
Yes.
I think this K reflecting in consideration.
Yes. Your question is very good. And in fact, in the literature, the procedure don't fix the number of cells. But in our case, we have the first problem that I described before. And there we know a priori the size of the graph. So you know the number of, that's why we fix the number. That's the reason why we do this. That's the reason why we do this. And to make the test, we look at in the literature for the best known solution, and we knew the number K reached by this technique. So we fix K to this value and try to improve this. But this is the first step in our process, because in developing the decision support system, the objective function is different than the one that we have here. But we use this grouping efficacy technique to get a good end on the meta-heuristic that we should use for the real problem, which is quite more complicated, because we have, in reality, we have two objective functions. So we have to deal with the problem with two objective functions instead of one. So it's a different context. Thank you very much.
There is another question? No? Okay. Thank you very much.
Thank you very much.